Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell apparently, and you'll get notifications for this series and a bunch of other ones on our channel. What we're doing today is multivariable calculus. Chapter 2 is double and triple integrals. Section 2.1 is double integrals over rectangles. We're starting and then we're going to build over general regions. Cleverly, we just find the region inside a rectangle and then we just define it that way, sort of. You'll see. This lecture, what we're just going to do is more iterated integrals to compute double integrals so that you can practice. Remember, you have to now remember substitution rule, integration by parts, partial fraction decomposition, trigonometric integrals, trigonometric substitution, hyperbolic substitution, with more than one variable. Let's try that. What is the double integral representing? It's representing if you have a positive function of two variables over a rectangle, it's the volume under the surface S and above the rectangle R. That's what this symbol means, and you can use iterated integrals to compute either way. Let's do that a bunch of times. Compute the double integral. What do we have? We have a function f of xy, which is x plus root y, and we have a rectangle which is 0, 1 cross 0, 3, so a, b, c, d. My function f, what does that mean? I can now use the iterated integral. If I do that, the integral over the rectangle of x plus y dA is equal to, by Fubini's theorem, I can use either. This will be, let's do the regular way to do it, the integral from 0 to 1, the integral from 0 to 3 of x plus root y. And then what was this? This was y, so we have dy dx. At the beginning, or always, it's a good idea to put the brackets in to help you remember now what did that do. I'm ignoring x and holding it constant, integrating with respect to y. Doing that, I get equals the integral from 0 to 1 of, what do I get? First of all, I'm integrating with respect to y, so I get xy in the first time. In the second one, square root is 1/2 exponent. Now I use the power rule. Y to the 1/2 integral dy is equal to 1 over 1/2 plus 1, y to the 1/2 plus 1, which is 1 over 3 over 2, y to the 3 over 2, which is 2/3 y to the 3 over 2. You should know those ones by now. This is plus 2 over 3, y to the 3 over 2, evaluated from 0 to 3. This is not dx. Don't forget your dx. I don't want to be doing Lebesgue integrals or Henstock integrals or what are those? Never mind. Equals the integral from 0 to 1 of, now luckily because I have y in both terms and I have a 0 there, I'm just going to put 3 in. That's going to give me 3x plus 2 over 3 times 3 to the 3 over 2, which is dx, which is what? What is 3 to the 3 over 2? This is 3 root 3, because it is 3 times 3 times 3 in the square root. I can move 2 of them out, and then I'm left with 1. The algebra never goes away, exponent laws. Equals. Now what do I get? So what did that give me? Sorry, I cleaned that up and then erased it. That got me 3 root 3, so those canceled. And I'm going to get this equals 3 over 2 x squared plus root 3x evaluated from 0 to 1, which is going to give me 3 over 2 1 squared plus root 3 times 1 minus 0, which is equal to 1.5 plus root 3. I'm going to guess you can rationalize and get a common denominator there. 2 root 3 plus 3 over 2. Next question. Example 2, we're going to use iterated integrals by Fubini's theorem. In this one, because of the symmetry of the function, it won't matter whether I use x or y at all. It doesn't seem like, because they're on the bottom and the top of one of the terms either way. So we're going to have to do both. Let's stick to our guns and do dy and then dx like we've been doing. Unless I would stick to, when I'm trying to first learn something, I stick to that. And unless there is some horrible, nasty integral, which you'll see eventually might well make me change, why would I change and do dx first? Just do dy and then dx, unless something, you get a horrible integral, which is integrated by parts or something. And then if you see the other one's easier, switch to that. Otherwise, no. This says that the integral over the rectangle of x over y plus y over x dA is equal to the integral from 1 to 4, the integral from 1 to 2 of x over y plus y over x dy dx. I'm integrating y first, x is a constant. This one, therefore, rewrite that. Baloney. These are the little things that I think trip you up every time. This is the integral from 0 to 2. This is the power rule, nothing more. But this is the magic one where the exponent is -1, so I use logarithm. But this is plus x to the -1y. That seems, I don't know, I like that a whole lot more. Now what I remind myself is it's power rule either way I'm doing it. I'm holding x constant. So this is going to give me the integral from 1 to 4 of x, the natural log of the absolute value of y, plus x to the -1 times 1/2 y squared, evaluated from 1 to 2 dx. Then what are we going to get? Putting that in by the fundamental theorem of calculus part 2, start over there. You have to write on Lord of the Rings. Don't do that. It's wood, by the way. It's not a poster. It's wooden. Someone commented, I like your poster. It's wooden. It's wood etching. Fancy. What are we going to do? We get the integral from 1 to 4 of what? I'm putting 2. Now we better be careful and put the 2 in where the y is. This gives me x log 2 plus x to the -1 times 1/2 2 squared minus from 1 x ln of 1 plus x to the -1 1/2 1 squared dx. Hopefully that screams out Pavlovianly, this is log of 1 is 0. That term's gone. What does that give me? Clean it up. That's going to give me the integral from 1 to 4 of x log 2 plus, what do I get? 2 over x minus, what did I get? 1/2 1 over x. If I didn't do that wrong. We got 2 minus 1/2. So that is what? That guy, if I didn't do that wrong. I have 2 of them, minus 1 x's here, and then I have minus 1/2 of a -1 x. Factor the -1 x out, I have 2 minus 1/2, which is 3/2. I have that guy, which is equal to, now what? Factor that however you want. Don't follow me. You should know how to do integrals at this stage. We're at an integral of x now. Put them in, compute. Now what do I get? Now I'm taking the derivative of, or the antiderivative with respect to x. This gives me log 2 over 2 x squared plus 3 over 2 times the natural log of the absolute value of x, evaluated from 1 to 4, which is equal to, can I squeeze it in? Let's see if I have enough room. This is equal to, don't be lazy, this is log 2 over 2 times 4 squared plus 3 over 2 log 4 minus log 2 over 2 1 squared plus 3 over 2 log 1. I don't care, that one's 0. Gone. What does that give me? Some hot mess, which gives me, I'm going to get 16 over 2, which is 8 log 2 plus 3 over 2 log 4 minus 1/2 log 2. I'm going to guess you could put that into a fancy exponent law and use log laws and put that in there and clean it up. Let's do that and then we'll give the final answer. Recapping the double integral of this function of x and y over this rectangle. We use the iterated integral dy then dx. Cleaning this up and using our log laws, we get, what I noticed is I have log 2. This is log 2 squared, this guy secretly. An exponent on the inside is number on the outside. And then I can get log 2, log 2, log 2, I noticed. Once I do that, I pull that down, the 2 cancels, and then I have 8 plus 3 minus 1/2 times log 2. Cleaning that up and adding fractions. Always, this is amusing, but nobody's scared of this symbol anymore. Oh, that was a terrible noise. Recapping, what I'm doing here is if I want to compute this function of 2 variables over this rectangle, I can use Fubini's theorem, and I integrated with the x first. Then what I did was I noticed that I had log 2 in every term by noticing log 4 is 2 squared. So I magically put that in there. Then I take this out using logarithm laws, and I add fractions, and I get 21 over 2 log 2. Now when you look at this hot mess, everyone's okay with this symbol now. And then I tell you to add or subtract 1/2 from 11, and you're like, what? It's like, yeah, 2 over 2 times 11 minus 1/2 is 22 minus 1 over 2, which is 21 over 2. This, you're just like, no! And this hot mess you're okay with. Let's do another one. Let's compute the double integral of sine x plus y over this rectangle. I'm pretty sure they put pi's now in there for convenient values of the trig function. This one, again, it seems fairly symmetric because I have x plus y. It won't really matter whether, when I use Fubini's, whether we do x or y first. So I'm going to stick to my guns and do y and then x, just like we've done for the other ones. This double integral of over the rectangle of sine of x plus y dA is by Fubini's the integral from 0 to pi over 2. The integral from 0 to pi over 2. Actually, with the limits you can't tell, I'll switch them. You want to see it again? Of sine x plus y of dy, then dx. There, I switched it back to dy dx again. What do I do with that? I hold x constant and I integrate with respect to y. That is going to give me the integral from 0 to pi over 2 times negative cos x plus y evaluated from 0 to pi over 2 dx. If you can't remember when that happens, take the derivative of this. You better get that back. Then, yep, I do. So I've got it right. The negative should be there. Then minus minus this, the first term will be negative. The last term will be positive. Professors like to switch that around in their head. Okay, I won't. I'll just write it out. By the fundamental theorem of calculus, is this the integral from pi over 2 of, this is negative cos of, what are we doing? We're putting y in there. So that should be x plus pi over 2. And that's what I was saying. And then this term will be minus minus. So then I want to flip that in my head. But I won't. Minus cos of x plus 0 dx. Now cleaning that up, I wanted to do that all in one step in my head, but I'll show you. Equals the integral from 0 to pi over 2 of, now what do I get? I get cos x minus cos of x plus pi over 2 dx. This is our a of x function again that they were talking about in the general theory in the previous video. And now we're going to integrate that guy with respect to x. Once we put all the y's in there, they're gone. We have a function of just x now. Integrate this. What do I get? Now I'm going to get the integral of cos is sine x. And this one is minus sine x plus pi over 2 evaluated at, technically that's a baby substitution rule. W equals x plus pi over 2, dw equals dx, equals 0 over pi over 2. And that is going to give me sine of pi over 2 minus sine of pi over 2 plus pi over 2 minus, be careful, sine of 0 minus sine of 0 plus pi over 2. I like what happened there cleverly. That gives me 1 minus 0 minus 0 minus 1, which gives me 1 plus 1, which is 2. If you subscribe right here, hit the notification bell, you'll get notifications for this series and a bunch of other ones on our channel. I'll see you next time. I can be at the end of the video. Guess what you're going to hear at the end of the video. Note to self, never do that again. I don't even know what I was doing anymore.